Hello, everyone. I'm Augusto, and I'm here representing the Polygon Miden team. And I'm going to be presenting the work that we have been doing for recursive verification on the rollup, on the Miden rollup. And Miden is a project that has both a completely new virtual machine and the rollup. And just a heads up, like most of the work that I'm going to be presenting here, it's actually a result of the teamwork, and I have done a little bit of this that I'm going to touch on it, but it's also like a lot of work of my colleagues. This is the outline of the talk. I'm going to talk a little bit about the approaches of recursive verification that we have considered, and then we're going to talk a little bit about the pros and cons of like the approaches that we have looked at, and then we're going to have a look at the requirements that we have settled for our rollup, and what are the goals that we have for our rollup in terms of performance, and then we're going to look for the verifier costs and identify if we can actually match the goals that we have in terms of performance with the verifier costs. Later on, we're going to look at some optimizations that we're implementing into the rollup, and I have like some results at the end. So the first approach that we have considered for the rollup and for like the recursive verification was to use a specialized circuit, right? So we would have the virtual machine in the bottom, and it's a general purpose virtual machine Turing complete. You can input to it any kind of program that you want, and as an output of the execution, you have your proof. And you can do the verification of that proof with a specialized circuit. And if you do that multiple times, you can aggregate multiple proofs, and then you have like a aggregation of multiple proofs. The second approach that we have considered is just to use the virtual machine itself to do the verification. And we can exploit the fact that our virtual machine is Turing complete. So we can just write a program that does proof verification and run that inside the virtual machine. We get a proof of execution from the virtual machine, and we basically achieve the same thing. So like these are the two approaches that we considered. And the question is like, what are the pros and what are the cons between these two implementations? So we have the question of like, we have the dimension of flexibility for the two approaches. And in this case, the virtual machine implementation is much better. And the reason why it's better is because we can actually run the verification procedure inside the virtual machine, and because it's a virtual machine, we can actually just run extra code alongside it, which means that we can basically do anything that we like after the verification or before the verification. Another dimension that it's actually important for us is the complexity. We usually try to maintain complexity at a minimum for everything that we do in the project, and that's a trade-off that we try to make things as simple as possible. In this case, the virtual machine approach would be more complicated because we have to have multiple implementations of the verification of like the circuit. There is a question of auditing, and in this case, we believe that having a single circuit, it's easier to audit instead of having multiple circuits, which would be the first approach, where we would have one circuit for the virtual machine and another circuit for the recursive proof verification. And the last dimension is performance. In this case, the specialized circuit would be definitely the best version for performance. And the recursive verification inside the virtual machine depends, and that's basically what the talk's going to be a little bit about. So those are the approaches that we considered. Let's talk a little bit about the requirements that we have for the rollup and the goals that we have set for ourselves. So we decided to go with the single virtual machine approach, basically because we get the extra flexibility, and we are using that extra flexibility to build the rollup. In our case, we allow the users to generate local proofs before they send the transaction to the network. And when we receive a valid proof into the sequencer, that does not necessarily mean that a valid proof implies into a valid transaction. So we need to run extra code to make sure that the data that it corresponds is packaged together with the transaction is actually valid. For example, to make sure that the account state that's being transitioned is the correct account state. So that's the reason why we decided to go with a virtual machine instead of a specialized circuit. We also have like some other requirements like security guarantees, and we're targeting 100 bits of security. And besides that, we also have like some expectations on the side of the programs that the users are going to be running, because we have local proving, so the users are generating proofs locally. We expect these programs to be from very small to medium-sized. And that's captured on the number of cycles that I have represented in the slides. This is something from a few microseconds to generate a proof to like 1 or 2 minutes on a Mac Air Pro. But like there is still like relatively small programs. And the question is, can we do proof aggregation, like recursive verification with these programs? We are targeting for ourselves 2 seconds recursive proofs aggregations, and the goal is to have 2 seconds in commodity hardware, so like laptops like this, and also into server, and like if we go with a beefy server with like tons of CPU cores, GPUs, and lots of memory, then we can actually increase the ratio of transactions or like proofs that we're verifying on the same batch. But in general, we are targeting 2 seconds for recursive proof verification. And the question is, what can we do in 2 seconds? Because that's what determines how much work we can actually put inside the program that's going to be doing the verification. And here I have like some reference points. These is the current numbers that we have for our virtual machine. And as a reference, I put it like Blake tree. But keep in mind that Blake tree is actually not part of our constraint system, so we actually cannot use that for recursive proving. It would be amazing because in 1 second we can actually do a lot with Blake tree. We currently use a version of Rescue Prime. We call it Rescue Prime Optimized, that takes 6 seconds to run that many cycles. And you guys probably know it, but you can think of cycles as like numbers of rows in a trace. So this is clearly not 2 seconds that I mentioned before in the previous slide. The thing that we're trying to do is to reduce the gap between the RPO hash function in respect to the Blake tree hash function. We believe there is a lot of performance to be gained in there. And what we're trying to do is implement a new hash function that's going to be more optimized. We are not going for Poseidon, which is the one that has the best performance right now, at least one of them, because there are some questions about the security of the hash function, and like there's some, it's just a conjecture, but it may not be sufficiently secure for the next 3-4 years. So we are sticking around with a different hash function that we are implementing and optimizing, and we believe, and we have prototypes for this already, but we believe they're going to be able to do this many rows in the trace in 2 seconds, which fits our target for the aggregation of proofs for the recursive proof verification. We're also doing some other things, like we're removing traces from, removing columns from the trace, which also improves performance and makes sure that we can actually reach our target. So this is the first thing, like this optimization gives us 2 to the power 17 cycles. And we want to do a 2-to-1 on commodity hardware, like a proof of aggregation when we do recursive proving. So the question is, can we do 2 proofs in that many cycles, or can we do 1 proof and half of those cycles? The rest of the presentation is basically the performance changes that we have done into the virtual machine and into the rollup to achieve this. So the important thing is actually to know where is the cost coming from on the recursive verification. And most of it comes from the SARC verifier. We do have some extra logic on rollup, but it's not the majority of the cost. And I believe, like, you all know these, but that's just like an overview of like the main points of the SARC verifier that we have to take in consideration when doing the performance analysis. And for our virtual machine, the design of the virtual machine is as such that we can actually analyze things independently in terms of hash and general computation. So just to understand why, I have like a tiny little diagram of the virtual machine, and these are the 2 important things of the architecture of the virtual machine that allows us to have like this independent analysis. And the main thing to notice here is that we have a chiplet, which allows us to do hashing operations concurrently. And we have another main processor that does general purpose operations. So we can run these 2 things in parallel inside the virtual machine, and because of that, we are going to analyze the 2 things independently. And if you guys remember, I had like some goals for the sizes of the input programs from the users. These are all the sizes, and we can clearly fit all the hashing operations that we need to do recursive proof verification on the number of cycles that we have targeted. So that's not our bottleneck. Our bottleneck is actually on the general computation, and that's where we have spent time trying to optimize things. And the next slides are just going to be about the optimization of these things. So again, this Arc verifier steps on a bird's eye view. I'm not going to be able to go over everything because I don't have enough time, but we're going to focus over these 3 sections of this Arc verifier. And we have to do these in 2 to the power of 16 cycles or rows in the trace. Starting with the fry layers, there are 2 operations that we care about, the folding and then doing the evaluation, proving the degree of the remainder polynomial. We have a general approach that we could do for the remainder polynomial, like a degree verification, which would be to run a entity inside the virtual machine, which would be extremely, extremely slow. So that's not what we do. What we actually do is that we do the entity and provide non-deterministically the inputs to the virtual machine. And we do all the computation using the barycentric form. So we can actually do the remainder, we can prove the degree of the remainder polynomial up to 8 in 3,000 cycles. So that is a little bit of the budget. The next thing that we have to take care of is about the folding. And here we have a trade-off, because if we do a folding of 2 to 1, we decrease the number of operations that we have to do in the virtual machine, but we increase the number of hashes because we increase the number of Merkle trees that we have to commit into. And there is a trade-off here. We decided to go for a fold factor of 4, and we have implemented native instructions in the virtual machine to support this. That way, we can actually do 1 layer with 3,000 cycles. The number of layers is going to depend on the input program size, and that depends on what the user is doing. So yeah, relatively quickly, but we have to analyze later on if that fits for the size of programs that we care about. Besides the folding, we also have to take care of the deep composition. And here the biggest thing is the random number generation and the arithmetic operations that we have to do. We basically did the same strategy. We implemented 2 new instructions to do linear combinations, and we also optimized the formulas that we use inside the prover to remove any redundancy and checks that we didn't need. The last thing that we have to take care of is making sure that we can evaluate all the error constraints in a sufficient number of cycles. And here we are doing something very interesting. We are trying to target 2 problems at once. We are doing this by implementing a new programming language, a high-level programming language that allows us to define traces for Stark-proof systems and the constraints between the columns. And that's a general programming language that can be used to implement any Stark-proven system. And we use it to do 2 things. We can have a centralized definition of the constraints of the virtual machine, and then we use the compiler to generate both the program that's going to run in the virtual machine itself and the prover that's actually going to be run by the user. So we only need to audit, in theory, the specification of the constraints in AirScript, which is much easier than doing that in Rust or any programming language. And we also have the benefit that we can actually run a compiler here and do some optimizations to make sure that we actually hit the 2 seconds target. So here's a summary of all the measurements that we have done so far. If you look at the bottom of the first column, we are in 36K rows for the Stark verification, and the only thing that's missing is the error constraint. That's the question mark, but that leaves us basically a budget of how many instructions we can spend doing the evaluation of the error constraints on the out-of-domain point. This is currently the open question. Can we actually feed the evaluations on 30K cycles? Because that's what is left in the budget, and we are pretty sure that we can do this. I hope you guys enjoy this, but it's super exciting work that we have been doing, and I think it's going to be super awesome to be able to have 2 seconds to do the recursive proof verification, because that's going to allow us to have a very quick block production on the rollup later on. And that's all that I have for you guys. Thank you for watching. I think 1 question?
Yeah. Hi, thank you very much for the presentation. Super interesting. I'm curious about the state of development of the recursive proving.
Yeah, okay, so we currently have a implementation of the backend that generates the Miden assembly code for the constraints, the error constraints. The Winterfell prover exists, and we can actually run prototypes in the virtual machine. The biggest piece that we're missing is that we don't have the whole virtual machine defined in AirScript yet. And the reason for this is because we're thinking about implementing GKR. So we're first going to finish the GKR, and then we're going to finish AirScript. So like there's some limitations there, like there's some bottleneck. Once we have GKR implemented, then we're going to finish the recursive proving.
Great. Last question. And it's potentially a bias that I have, but I have the idea in my head that it's pretty novel to be able to make like client-side proving. And so potentially what were the bottlenecks that were there like 1 year ago? Or what happened that enabled us to make client-side proving a thing now?
Okay, there's quite a few things, right? Like the size of the field that we are using, some optimizations, barycentric representation, GPU acceleration. There's just like a lot of work that has been done by dozens of people that has been going into this and making sure that we can do everything fast. So it's just like a lot of engineering work that goes into it, and there's many small pieces that helped us. Okay. Thank you very much.